Previously, we learned about Newton's laws in Lecture 3, but in the absence of mass. Today, we are going to look at what happens when the mass at a point is non-zero. That is, we are going to look at the sum of forces being equal to mass times acceleration, where the mass is non-zero. Remember that here, F are the forces acting on a point, always defined to be positive if the force would cause a positive acceleration. And A is the acceleration, the second time derivative of the position of the point, defined to be positive if the acceleration is to the right. The acceleration A is also the first time derivative of the velocity, v sub m, of the point. Lastly, remember that v sub m of the mass is always assumed to be measured relative to what is called an inertial reference frame. In the case of the spring mass damper system, the inertial reference frame is the wall. That is, we measure velocities with respect to the wall. This diagram could represent a lot of things, like the shocks on a car or bicycle, or even this slinky, where now we think of the bottom of the slinky as having mass, and the rest of the slinky as having the spring characteristics. If I hold the slinky horizontally, then gravity has no effect on the linear motion. But if I hold it vertically, then of course the slinky will oscillate, and that means that gravity is acting as an external force on the system. The slinky is a good example to keep in mind because the model we choose to use really depends on what behavior we are trying to model. If the slinky only oscillates like this, then probably the model that I just told you about will do a good job. If, however, we create extra oscillations like this, then probably it won't do such a good job because there are too many oscillations in the system and such a simple model won't capture them all. Hence, your engineering judgment really matters. You cannot just blindly write down a model and expect it to be valid. Let's look at a model of a mass with a spring and a damper. The sum of the forces are equal to the mass times acceleration. So we get F external minus the spring force minus the damping force because of our sign conventions. And those are equal to mass times acceleration, which we know is equal to mass times the second time derivative of the position of the spring. We already know from Lecture 3 that V sub d is equal to x sub s dot, giving F external. And now we're going to plug in the constitutive law, and we're going to plug in the damping part of the constitutive law as well. Now that is equal to mass times the second derivative. And now notice that x sub s shows up everywhere in this equation. Now if we solve for x sub s double dot, we get x sub s double dot is equal to minus k over m x sub s minus b over m x sub s dot plus f external over m. This is a linear constant coefficient second order ordinary differential equation in the position of the spring x sub s. We know that we need a first order ordinary differential equation if we are going to use Euler integration from Lecture 4 and the analytic solutions from Lecture 5. So we need to convert this system to a first order ODE. To do so, it is helpful to note that the equation can be rewritten as x sub s double dot is equal to f, some function of x sub s and x sub s dot. Now, we can rewrite this double time derivative as x sub s dot, but taking d dt of that. And that is also equal to f of x sub s dot. This we are going to relabel as just v because it'll help keep track of things in a nice way. This means that v dot is equal to f of x sub s v because we've relabeled x sub s dot, and we know that because of the labeling, x sub s dot is equal to v. This is now a first order differential equation where the relabeling allows us to see that on the left-hand side, we have the time derivative of two quantities, and on the right-hand side, we have a function of those two quantities. This exercise of converting from a second-order differential equation to a first-order differential equation is something that you will do a lot as an engineer. It's worth practicing. What should you remember from today? First, Newton's equations allow you to incorporate mass into a linear, constant coefficient ordinary differential equation. Secondly, hopefully the slinky convinced you that when you have mass, you should expect the possibility of oscillation. And third, that ODEs have to be converted into first-order differential equations, which will mean increasing the number of differential equations.